Hello everyone, we will talk about the determination of equivalent circuit parameters today. So we have some tests similar with the transformer equivalent circuit parameters determination, and the first test will be the no load test. For no load test, the induction motor will rotate freely, and we can obtain some information about the rotational losses and the magnetization current which is flowing through the XM through the no load test. So when we remember the equivalent circuit, we have R1, X1, and with the excitation branch, we have RC and XM, and this four parameters represents the stator components. Then for the right side, for the rotor side, we have X2 related to the leakage flux reactance and R2 and the last resistance R2 1 minus S over S circuit can be used to clarify the operation during the no load test. This is the modified equivalent circuit, so it is very similar with the classical equivalent circuit of the induction motor, but we divided into two parts our last resistance, which represents the rotor side, R2 and R2 1 minus S over S. So when we examine the circuit during the no load test, we have Nm. It will be very close to Ns. Why? Because there is no load at the output side. So when we remember the torque speed characteristics, Nm will slide through the Ns. So if they are very close to each other, we can say S will be very, very small. So during the operation of no load, S is very small, and from here we can say our last resistance in the modified equivalent circuit will be very large according to R2 and X2. So the circuit can be modified. We can eliminate the R2 and X2, and R2 1 minus S over S can remain only in the circuit. So we can draw our, according to the relation between the components during this operation, to be able to make an analysis about the no load test RC and XM. And for the right side, we can draw only the R2 1 minus S over S. And the input voltage will be phase because we have the per phase equivalent circuit. And then according to our last version, simplified version, we can re-examine and we can see the relation between the parallel components of XM, RC, and R2 1 minus S over S. The smallest one with respect to others will be the XM. So XM will be very, very small with respect to RC and R2 1 minus S over S during the no load operation. So because of this, during the no load operation, we can simplify our circuit. We can analyze these components XM we face and I1. So the total impedance during the no load test, of course, the magnitude of the equivalent impedance will be V phase over I1. And for the equivalent impedance, what we have? Only R1, X1, and XM. Okay, so for the second test, to determine the equivalent circuit parameters can be the DC test. So for DC test, we have only the DC input voltage through the circuit. So when we apply DC voltage, all the reactances and the operation related components will be neglected. So only the stator winding resistance will remain in the circuit. So if we apply a DC voltage through the terminals, and if we measure the input current and the voltage, for the source, we have three-phase induction motor. So through the induction motor, we can say the circuit will include only the stator winding resistance of R1. All the other parameters can be neglected from the equivalent circuit because the system will not operate when we apply the DC voltage to the terminals. So we have a three-phase connection. So in that case, to find the average value of R1, we can use 2 of 3 phases. So in that case, the current flowing through here and the voltage we apply to the circuit will give us 2R1 will be equal to voltage and the current divided by current. The third test will be the locked-rotor test, or in other words, blocked-rotor test. For that one, we have the similar operation of short circuit test of the transformers. And we will stop the operation during that part. So the system will be stationary, so there will be no NM. NM will be 0. So if NM is 0, the sleep must be 1. And from here, the last component of the circuit, R2 over S, will be equal to R2. And we know it is very small value. So in terms of the circuit, R2 and JX2, which are parallel connected with XM and RC, but when the sleep is equal to 1, this part will be very small with respect to RC and XM. So our circuit can be R1, X1, X2, and R2. Not R2 over S for that part because sleep will be 1 during that operation. X1, X2, and R2. Again, we will apply V phase and I1. During that operation, of course, our input voltage V phase will be smaller than the rated values, but in addition to that, during this locked-rotor test, our test frequency will be also dropped. So it will be generally 25% of the rated frequency during that operation to be able to find R1, X1, X2, and R2 relations. So the rotor frequency will be equal to test frequency because we don't have any excitation branch in the circuit. All the components are connected in series, and we can calculate the locked-rotor impedance. During the locked-rotor operation, the magnitude of the impedance can be calculated with the V phase over I1, and which includes Blocked-rotor resistance and X Blocked-rotor prime. Why prime? Because we need to change our test frequency to the normal rated frequency values. So we will calculate the referred, changed, adjusted Blocked-rotor reactance initially. Okay, what about the Blocked-rotor resistance? According to our circuit, we have two resistances, which are R1 and R2. For the X Blocked-rotor prime, according to equivalent circuit, we have X1 and X2. And these are also must be prime because of the frequency conversion. What about the actual value? So the X Blocked-rotor can be calculated with the ratio between the frequency F rated over F test times Blocked-rotor prime. So the actual value, rated value, can be calculated with this expression. Okay, let's continue with an example to understand these calculations. For example, if we have 7.5 horsepower induction motor, what's that value? This is the rated output power. And we have 4-pole, 208 volt, which is the rated terminal voltage face to face, 60 Hertz, and design A type induction motor. What's the meaning of design A? The reactance, leakage reactance ratio between the stator and the rotor part, we have different designs from design A to F. For example, for design A, the stator leakage flux reactance will be equal to X2 and it will be half of Blocked-rotor reactance. So here we can calculate the total reactance in the system, but if we want to separate as X1 and X2, we can check the design type of the machine. Y connected induction motor we have, and its rated terminal current is 28 amperes. So test results are also given. For example, for DC test, we have a DC voltage of 13.6 volt and the DC current will be 28 ampere, which is the rated value. During the no load test, for 3-phase, terminal voltage will be 208 volts and it must be the rated value of the induction motor. For the phases IA, IB, and IC, for the phases, the currents of the induction motor for each line is measured as 8.12 amperes, 8.20, and 8.18 amperes. The applied voltage frequency is 60 Hertz, which is the rated value also during the no load test. And the input power for 3-phase is measured as 420 watts. The next test results for Blocked-rotor. The terminal voltage during this test is 25 volt, which is smaller than the rated value. It can change between 15 to 25 of the rated voltage. And IA, IB, and IC, which are the line currents during the Blocked-rotor test, and it must be close to the rated current of the induction motor. And it is measured as 28.1, 28, and 27.6. The frequency during this test is 15 Hz and the input power 920 watt during the Blocked-rotor test. So let's calculate some parameters. For example, from the DC test, we can start with the calculation of R1. So for R1, DC voltage during the DC test 2 times IDC, because we will connect 2 of the 3 phases in series to apply this test when the system is Y connected. So from here, according to given values, 13.6 volt divided by 2 times 28, 0.243 ohms. So this R1 also in the during the calculations can be neglected because of the small value of R1. But it can be determined as 0.243 from the DC test. Then let's continue with the second test, which is the no-load test. So from no-load test, first of all, we can calculate the current, because 3 phases are given, so average current for the calculations should be determined. So during the no-load test, the average current can be calculated with 8.12, 8.20, 8.18 divided by 3 will be 8.17 amperes. And the equivalent impedance during the no-load test is, according to our analysis we discussed previously, it is R1 and X1 XM. The R1, when we check the R1 value, it is 0.200 something. So because of this, we can say that equivalent no-load impedance magnitude will be nearly equal to X1 and XM. So we phase no-load voltage, no-load test voltage divided by IL average we must use. So 208 volt is given as the phase no-load terminal no-load voltage, and the system is connected in Y. So because of this, as the phase voltage, we must use 208 divided by square root 3. And for the denominator, we have 8.17, the average line current. And because of the Y connection, line and phase currents must be equal to each other. From here, X1 and XM can be calculated as 14.7 amperes. Then the last test results should be examined. From the Blocked-rotor test, first of all, we can calculate the average line current. So IL average during the Blocked-rotor average current can be calculated. The values for the ABC phases are 28.1, 28, 27.6 divided by 3, 27.9 amperes will be the average Blocked-rotor current. What about the impedance? Blocked-rotor impedance magnitude can be calculated by dividing Blocked-rotor voltage to IL average. The voltage, terminal voltage, is given as 25, and we have a Y connection, so I will divide to 3, square root 3, and the current is 27.9. For the phase and the line, they are equal to each other, and from here the impedance can be calculated as 0.517 ohms. So this is the total impedance during the Blocked-rotor test. We can calculate the resistance and the reactance values. So our Blocked-rotor can be calculated as the real part of the impedance. So our Blocked-rotor will be Z Blocked-rotor times cosine theta. So let's calculate the theta power factor first of all. To calculate it, we can use the input power. So the theta will be cosine minus 1 of input power during the Blocked-rotor test, because we are examining the Blocked-rotor analysis. Input power divided by 3 times V phase IL. So cosine minus 1, 920 watt is given as the input power during this test. 3 times for the phase voltage, 25 over square root 3 because of the Y connection, and our current will be 27.9. From here, the theta will be 40.4 degrees. So we can calculate the resistance. Our Blocked-rotor, the impedance value 0.517 and the cosine 40.4 degrees. 0.394 ohms will be the total of resistance of the circuit, R1 and R2. So this is also equal to R1 and R2. And we know the value of R1. So from here, R2 can be calculated. R Blocked-rotor and the R1. Blocked-rotor 394, 0.394 minus, as we calculated from the DC test, 0.243 will be the R1. So R2 can be calculated as 0.151. What about the reactance of the circuit? Similarly, X Blocked-rotor will be the imaginary part of the impedance. So Blocked-rotor prime during the test, first of all, we will calculate Z Blocked-rotor times cosine sine 40.4 degree. So from here it can be calculated as 0.335 ohms. And the rated value of the locked reactance can be calculated with the ratio of frequencies. So Blocked-rotor reactance will be F rated divided by F test times the test results. The rated frequency is 60. The test frequency during the Blocked-rotor test is 15 times 0.335 will be the test result. So Blocked-rotor reactance from here will be 1.34 ohms. And if we have a design A-type machine, that means X1 must be equal to X2, and it will be half of Blocked-rotor reactance. So that means X1 and X2 will be 0.67. Still, we have a missing parameter. What is it? After the no-load test, we have calculated X1 and Xm. So after we calculate X1, now we can find the Xm value. So after that, from the no-load test, we have the value of X1 plus Xm. They are together 14.7 ohms. So Xm can be calculated 14.7 minus X1 value 0.67. That means 14.03 will be the Xm itself. So let's check the equivalent circuit. So we have R1, X1, Xm, X2, and R2 over S. So for these parameters, according to our calculations, we can write their values. For example, R1 will be 0.243 ohms. This is 0.67, 0.67 ohms for X1 and X2, and 14.03, and the last one will be 0.151 divided by S. So this is the equivalent circuit with the parameters after we examine the determination of equivalent circuit parameters using DC test, no-load test, and the Blocked-rotor test. Thank you for watching.